everybody, it's Mrs. Harbin. We're doing video note 7.2, which is the mole and conversion problems and percent composition. So we're going to figure out how to use the mole concept for dimensional analysis and calculate percent composition. Right? So make sure you read chapter 8, sections 8.1 to 8.4, so you get this all going. Alright? Please remember to keep calm and calculate moles. So 1 mole equals 3 things. Avogadro's number of either atoms, molecules, or formula units. Those are the parts we use in chem. So those are the things that you're going to have to use when we do chemistry mole conversions. Okay. Next, make sure to know that 1 mole equals 22.4 liters, but that's only of gas at standard temperature and pressure. And finally, make sure you know that 1 mole equals the mass in grams from the periodic table. So once you know these 3 things, we can use these as conversion factors. So let's get busy. Oh, look, they're up in the corner. So we need to convert 12.5 grams of carbon dioxide into liters of carbon dioxide. So your best bet is to start with your given. We're given 12.5 grams. We're trying to find liters. So take 12.5 grams of what? CO2, right? Please give it a number and a label. Grams of CO2 is what we need to convert. And we know that we can change it to moles of carbon dioxide because of this conversion factor. And then moles of carbon dioxide can change into liters of carbon dioxide because of this conversion factor. So 1 mole equals grams. Okay, what number do I put there? Well, you go to the periodic table, you get 12.01, 16.00 times 2, 44.01 grams of carbon dioxide. Okay, that came from the periodic table. Then we say for every 1 mole of carbon dioxide, it takes up 22.4 liters of space. Then you plug that in your calculator, 12.5 divided by 44.01 times 22.4, and you get 6.36. 6.36 what? Well, let's see. Grams cancel grams, moles of carbon dioxide cancel, liters of carbon dioxide is what's left. Okay? Alright, let's see if there's more we can do. Convert 19.9 liters of oxygen to grams. Okay, so this is given. This is find. 19.9 liters of oxygen. Okay, here's what you gotta be careful of. Oxygen's an element. When oxygen's an element, then you have to use it as a diatomic. Okay. So liters can change into moles, and then moles of oxygen can change into grams. So now we just need to use our conversion factors. For every 1 mole, there's 22.4 liters. Okay. For every 1 mole, there's go get grams from the periodic table. So to go get grams, now it's O2, so I have to use grams as of O2. So liters cancels liters, moles cancels moles, and I plug this in my calculator, and I get 28.43 grams of O2. So I did 19.9 divided by 22 times 32.0, and I get 28.43 grams. Okay, so that's using your conversion factors, right? Hey, look, we have a lot of formula units. Given a lot of formula units, we have to change those into grams, okay? So start with the given, 9.55 times 10 to the 21st, and I'm going to use the nice way to abbreviate it, 4 U's of MgOH2. Very important that we know how to write the formula for magnesium hydroxide. Okay, plus 2 minus 1 minus 1, we need 2 hydroxides. Alright, so then we need to change formula units of magnesium hydroxide into moles of magnesium hydroxide. Every number needs a unit and an identity. Okay, and then for every 1 mole of magnesium hydroxide, we get grams of magnesium hydroxide. Right. So let's plug in some numbers. 1 mole equals this conversion, Avogadro's number of formula units. Okay, and then 1 mole equals, we got to go get grams from the periodic table. So I need to go get grams for magnesium hydroxide. So I look at the periodic table, and I've got 24.31 for magnesium, plus 2 oxygen, 32 grams for oxygen, plus 2 hydrogen, 2.02 grams for hydrogen, 3, 4, 2, 4, 7, and then 5. Looks like it's 57.43 grams of magnesium hydroxide. And then I got to plug this in my calculator. So I hit 9.55. And then I hit the second button and the double E button to plug in that 21. 9.55 E21 divided by 6.02 second E23 times 57.43. And I get 0.91 grams of magnesium hydroxide. Okay, so calculator time. We need to convert 3.55 liters of chlorine gas into molecules. So I start with the given 3.55 liters, and chlorine gas is Cl2. Please be careful of that, Cl2. 8 liters of chlorine, change it to moles of chlorine, and then moles of chlorine can change into molecules. I'm going to go with MC for molecules. Alright, oops, equals. So 1 mole is 22.4 liters. 1 mole is Avogadro's number of molecules. So then I plug this into the calculator, and I get 1.71 times 10 to the 24th. That's a lot of molecules of chlorine gas. Okay, so lots of examples so far. Can they be harder? Yeah, they can be a little bit harder. If we want atoms, but we're not given that our smallest particles are atoms, then we have to convert one more step beyond. Okay, so for instance, if you have 13.7 liters of water, we want to know atoms of H in there, so just atoms of H. So I could say, all right, liters of water can change into moles of water using my conversion factors. And then moles of water can change into molecules of water using my conversions. Here's the next step. For every molecule of water, there are atoms of hydrogen in it. Okay, so then math-wise, I would plug in 1 mole equals 22.4 liters, just like I did before. 1 mole equals Avogadro's number of molecules, as usual. Here's where it gets a little tricky. This is dependent just on the formula. We're already into tiny particles. And so if I only have 1 molecule of water, so this unit has to cancel. How many atoms of hydrogen? Well, there's 2. Because in H2O, for every one of these, there are 2 H's. So that's why I have to do this last conversion. Okay, so liters cancel liters, moles cancel moles, molecules cancel molecules. We're left with atoms of hydrogen only. And then plug that in 13.7 divided by 22.4 times Avogadro's number times 2, and you get 7.36 times 10 to the 23rd atoms of hydrogen in that. So this last step depends on the chemical formula of water, but everything else is a mole conversion. Okay, how many ammonium ions are in 2.5 grams of ammonium nitride? Well, first we need a chemical formula for ammonium nitride. So we have NH4, the positive charge, and -3 because it's got so we need 3 of these in our formula. Okay, so now we have 2.59 grams of ammonium nitride, and we want to get rid of grams of ammonium nitride and change it to moles of ammonium nitride. There's a 3 there. Okay, that gets us to moles, and then moles of ammonium nitride can change into formula units of ammonium nitride. But we're not done then, because I want just the ammonium ions in that. Well, there's actually more ammonium ions, because for every formula unit of ammonium nitride, there's actually some ammonium ions in it. Okay, well, let's fill in some numbers. 1 mole equals grams. I got to go get grams from the periodic table. So there's 2 nitrogens and 12 hydrogens, so I get 68.16 grams. And then for every 1 mole, there's Avogadro's number of formula units. Okay, here's where it's the tricky part in this one. For every 1 formula unit of ammonium nitride, there are 3 ammonium ions. This last step is dependent on the chemical formula, and that's it. So grams cancel grams, moles cancel moles, 4 millunits of ammonium nitrate cancel. You're left with ammonium ions. I want you to calculate that one and put it in your notes. Okay, simpler questions. So that is as complicated as it gets right there. All right, so is there simpler things? Well, we want to know how many liters, or what's the volume of, I can't get this to change to red. Yay, it's red. Okay, so NH3 is ammonia. Now, I know we would call it nitrogen trihydride, but I want you to get to know that ammonia is NH3. So we're given moles, and we're asked to find volume, which is liters. So we have 3.59 moles of NH3. Well, that means we're already in moles. We need liters. So moles of NH3 can turn into liters of NH3. Hey, this is only one step because I only have to use one of these conversions because I already have moles. If one of the units is in your given is moles, or your find is moles, it's a one-step problem. Okay, so moles of ammonia cancel. 3.59 times 22.4 is 80.42 liters of NH3. Oh, one step, easy peasy. All right, hey, look, it's atoms of calcium. So this is given. Find moles of calcium. All right, so, well, let's start with our given, 5.9 times 10 to the 23rd, and that's atoms of calcium. Okay, well, I want to get rid of atoms of calcium and change it into moles. Hey, stop right there. Why? Because you only need to use one of these in it. So 1 mole is Avogadro's number of atoms, because the smallest part of calcium is atoms. So then I put in the 5.9 E23 divided by 6.02 E23. I get 0.98 moles of calcium. All right, so all of this stuff leads to more stuff, but these are called mole conversions because you have to use one of these 3 pieces of information. You might have to use more than one, and then you might only need 1, you might need 2, and you might need to know chemical formulas. All right, so next thing is percent. Percent is always part over total. So let's talk about Thanksgiving. How many people in your class ate too much turkey for Thanksgiving? Well, if 16 of you in class ate too much turkey, then the percent is 16 part of the people who ate turkey over total. All right, and that gives you a decimal number, and then you have to multiply by 100. So 16 over 24 equals 0.6666, repeating, right? And then we multiply that by 100 to make it percent. So it's 66.67% ate too much turkey. All right, percent is always part over total. Remember that, part over total. So now what if we want to know percent, but we're talking about chemistry stuff? All right, percent, but we're talking about chemistry stuff. Well, what we want to know the percent of? We might want to know the percent of each element in a compound. Okay, what if you know the chemical formula? Percentage of CO2. Okay, so that's how much of each element. So percent of carbon. Well, I don't have any numbers here, but guess what I can do? I can go to the periodic table and get the numbers. So there's 12.01 grams of carbon for every 44.01 grams of carbon dioxide. And then if I multiply that by 100, I'll figure out what percent is carbon. It's 27.29%. So you can go get it from the periodic table. So carbon dioxide has 27.29% carbon. What about oxygen? Well, there are 32.00 grams of oxygen for every 44.01 grams of carbon dioxide. Now, where did I get the 32? Periodic table. Where did I get the 44.01? Periodic table for the total. Part over total. Times 100. And then you get 72.71% oxygen. Okay, so you can find percent of each element in a compound by taking part over total, part over total, part over total. Don't you forget it. Okay, so let's see if we can say, well, what if we don't know the chemical formula of our compound because we're just using lab data? Well, here's the lab data. 95 gram total. Okay, 46 grams carbon, 54 grams oxygen. Easy peasy. Percent of each element, percent of carbon is the 40.6 grams of carbon over the 95.0 grams total. All right, times 100 gives us 42.74% carbon. Okay, percent oxygen? Well, there's 54.4 grams of oxygen over your 95.0 grams total. All right. We don't know the chemical formula. That's why I'm not writing a chemical formula there. And you get 57.26% oxygen. So wait a second. If I go back to the slide before, I find out that carbon dioxide has this percent carbon, this percent oxygen. But this compound has this percent carbon and this percent oxygen. Are they the same compound? And that's what's cool, is chemical analysis tells us that this is a different compound. In fact, this is carbon monoxide, and that compound before was carbon dioxide. So the percentages can help you identify your stuff. Okay, so what else can we do with the percentages? Well, we can figure out, I want to isolate how much oxygen is in this sample of ammonium nitrate. Okay, so there's a couple ways to do this problem. I'm going to do it using the percent. Okay, so in this compound, I can figure out the percent of oxygen overall. So I would take the mass of oxygen, so 3 times 16.00, because there's 3 oxygen, so there's 48.00 grams of oxygen for every total nitrogen plus 4 hydrogen plus another nitrogen plus the 3 oxygen. I find out 80.06 grams in NH4NO3. It's ammonium oxide. I'm sorry, ammonium nitrate. And I find out that there's 59.96% oxygen in every sample of ammonium nitrate. What if I only have 35 grams? So in 35 grams of ammonium nitrate, how much of that is oxygen? Well, if I take, oops, I don't need that. If I take 0.5996, because that's the percent of oxygen, then I find out in this sample that there would be 20.98 grams of oxygen in that sample. Okay, so that's one way to do it. Another way to do it is I say, all right, if I have 35 grams of the total compound, ammonium nitrate, and then I know that for every 80.06 grams of ammonium nitrate, that's 1 mole of ammonium nitrate, right? And then I could say, well, for every 1 mole of ammonium nitrate, there are 48 grams of oxygen. Okay, if I do that, I find out I get the same answer by calculating. Okay, so you could do percent problems a couple of ways, but you have to know that the mass of 1 mole comes from the periodic table. Right? So you could do percent. The mass of oxygen in a mole is the total mass from the periodic table of just that element. Okay, so I use this number here, I use this number here, and I realize that it's 1 mole for each of those. Okay, so to review, moles are groups of elements. Groups of particles. They have Avogadro's number of particles. All right, these are the smallest pieces. Go to the periodic table, get grams. Always go through moles when you're converting. 1 is the number that goes with moles. Percent is part of the total. It's a lot to do, but I think you can do it. Make sure you read chapter 8 so that you can do mole conversions and calculate percent composition. All right, so we're going to be practicing in class. See you soon.